Hello and welcome. So, you're a civil engineering student, and that big oral exam is just around the corner. Well, you're in exactly the right place. We're going to walk through how to build a clear, confidence answer for one of the most fundamental topics you're going to face: building thermal physics. Let's dive right in. Just imagine it for a second. The examiner looks at you and asks that exact question. Now, the goal here isn't to just spit back a bunch of formulas. It's to show them that you really get it. The concepts, the why. This whole explainer is designed to be your answer, a logical story you can tell with confidence. So here's our game plan. We'll start with the big picture, why this stuff even matters. Then we'll nail down the essential vocabulary, the terms your examiner absolutely expects you to know. After that, we'll connect the dots to real-world problems like thermal bridges and condensation. We'll finish up by talking about the ultimate goal, thermal stability, and I'll give you a simple checklist to structure your answer perfectly. Okay, first things first. Let's start at the very beginning. If you're asked to explain the core purpose of building physics, you need an answer that's both concise and powerful. Really, it all boils down to two main things. First, it's about people. That's why we build things, right? We want to create indoor spaces that are healthy, comfortable, and stable. But second, it's about performance, and honestly, about money. A well-designed building directly impacts how much energy you need to heat and cool it, and that hits the wallet over the long run. So remember, it's always about human comfort and economic efficiency. All right, next up, you have to speak the language. Nailing these three key terms shows the examiner that you've got a solid grasp of the fundamentals. First is thermal conductivity, or lambda. Now, this is a property of the material itself. It's baked in. Just think of it as how good that material is at letting heat travel through it. A low lambda value, like you'd find in insulation, means it's a poor conductor of heat. It's like a really thick, effective thermal sweater. Something with a high lambda, like steel, lets heat pass through super easily. This is the starting point for picking your material. Now, building on lambda, we get to thermal resistance, or the R value. This isn't just about the material anymore, it's about how you actually use it. The R value depends on the material's lambda and its thickness. So if you take a great insulator, something with a low lambda, and make it really thick, you're going to get a nice, high R value. This number tells you how well a specific layer in your wall is doing its job. And that brings us to the U value. Think of this as the final grade for the entire assembly. It measures how much heat gets through a whole section of the building, like a wall with all its layers, or a window, or the roof. It takes everything into account. And for the U value, the golden rule is lower is always better. It tells you how much energy you're losing, and this is the number that building codes and regulations are often built around. And these terms, especially that U value, are front and center in the official criteria used to evaluate a building's performance. As you can see, the U value is often listed right at the top, but it's part of a bigger picture that looks at everything from airtightness to overall thermal stability. Okay, so now that we've got the vocabulary down, let's talk about where things can go wrong. You can design a wall with a fantastic U value, but its performance can be completely ruined by thermal bridges. These are basically the weak spots, the Achilles heel of a building's thermal envelope. So where do they pop up? Well, they happen anywhere that continuous layer of insulation gets broken, squished, or just isn't there. We're talking about corners, where walls meet floors, around windows, and a classic example is a concrete balcony that sticks right out of the building, creating a direct path for heat to escape. This diagram here shows exactly what's happening. On a nice, flat wall, heat flows in one direction, straight out. But at a corner, the outside surface is bigger than the inside one, so the heat flow spreads out and it escapes much faster. It's literally a thermal highway for heat to leave your building. And here's the real kicker. Because all that heat is escaping so quickly, the temperature of the inside surface right at that thermal bridge drops a lot. It becomes the coldest spot in the room. And that cold spot sets the stage perfectly for our next big problem. And that problem is condensation. You see, warm indoor air can hold a lot of moisture, but when that warm, humid air touches the cold surface created by a thermal bridge, the air cools down instantly, and cold air can't hold as much moisture. So that water has to go somewhere, and it condenses into liquid, right there on your wall. Now, this is way more than just a little fog on a window. When this happens over and over, that moisture starts causing serious damage. It can wreck the strength of materials like wood and drywall, make a room feel damp and unusable, and of course, lead to ugly stains and peeling paint. But it gets worse. Those damp, dark conditions are the perfect breeding ground for mold. And this is where it gets really serious. Mold isn't just ugly, it releases spores that contain mycotoxins, some of which are actually carcinogenic. So a simple design flow, a thermal bridge, can lead directly to a serious health hazard. Explaining that cause and effects chain is absolutely crucial for your exam. Okay, so we've identified the key problems. What's the end goal here? What are we striving for? It's all about achieving thermal stability. And that means designing a building that performs well not just on the coldest day of the year, but all year round. Think about it. In the winter, thermal stability means the building holds onto its heat. If the furnace breaks or the power goes out, a stable building cools down much, much slower. In the summer, the goal is the complete opposite. We want to resist overheating. The building needs to shield the inside from that intense summer sun to stay naturally cool. A great design does both. Overheating in the summer comes from a few places. You've got the sun blasting through the windows, which has an immediate warming effect, but you also have the roof and walls soaking up heat all day long, and that heat slowly radiates into the building later on. And the key to managing both of these challenges is the building's thermal mass. Heavy, dense materials like concrete or brick are like thermal batteries. In the summer, they absorb all that daytime heat, slowing it from getting inside. And in the winter, they store heat from your heating system, slowly releasing it back into the room. This thermal mass acts like a giant stabilizing flywheel for your indoor climate. All right, let's put this all together. Here's a clear, simple structure you can use to frame your answer in the exam. Here's your 4-step game plan. Step 1, start with the big picture mission. It's all about comfort and efficiency. Step 2, define the key terms, lambda, R value, and U value, to show you know the basics cold. Step 3, explain the real-world problems, making that critical link between thermal bridges and condensation. And finally, Step 4, describe the holistic solution, which is designing for year-round thermal stability. So when you walk into that exam, here's what you absolutely have to remember. Don't just list facts, explain the cause and effect. Always tie the theory back to what's actually happening in a real building. Make that direct, unbreakable link between a thermal bridge, the cold spot it creates, and the risk of condensation and mold. Stress that thermal stability isn't just a winter thing, it's for summer too. And always, always bring it back to those two main goals, making people comfortable and saving energy. If you can tell that story, you'll be in great shape. Good luck.